Welcome back, Physics 30. This is the combined FM1.3 motion at constant acceleration and 1.4 solving problems involving that. So we've looked at uniform motion, looking at velocity as displacement over time. Then in 1.2 we looked at acceleration. Now, using that idea of acceleration, we can derive a bunch of equations to use in a variety of scenarios. There we go. I'm not going to go through how they are derived. We're just going to simply look at how to use those equations. So understand how to use them and then solve word problems involving that. So we'll now examine motion in a straight line when the magnitude of the acceleration is constant. So the acceleration is constant, so you're increasing or decreasing by a constant amount. That's when these would come into play. So notation in physics varies from book to book, and different instructors use different notation. The notation will be slightly changed here, so we'll use VI for V1, so initial velocity, and VF for V2, meaning final velocity instead of V2. So we've seen this one. This is basically the acceleration equation. If I rearrange this and solve for VF, I end up with that, so that would be a handy one to use. I could also rearrange this one and solve for VI, or initial velocity, and I get this. Now these, if you haven't received it already, you will get a formula sheet that has all of these equations on them. So this is good, and if we don't have time, so when we don't have time as a variable, so I'll just write here, when no time, we can use this, dealing with the displacement instead of the time. Okay, and this one here, when we don't know V final, this is a good one to use. It involves V initial and acceleration in the time, and quite often your initial velocity is 0, so this part of the equation disappears. This is one we looked at already. It's basically velocity equals displacement over time. Sometimes it's referred to as average velocity. Another way we can figure out average velocity is if I add my V initial and V final divided by 2. And then lastly, D is equal to VI plus VF over 2 multiplied by T. All right, so these equations are not valid unless my A value is a constant number. So we're either accelerating or decelerating by a constant amount. So if we look at the process of solving word problems, read the whole problem, make sure you understand it, then read it again. Decide on the objects under study and look at what the time interval is, if you are given time. Diagram often works. I like to do diagrams. This is a key one. Write down what you're given and write down what you're trying to find out. That's a big one. Look at the variables. Are you given initial velocity? Are you given acceleration? What are you given? What physics applies here? What is your approach? And then more importantly, what equations can you use? So quite often you're given all the variables except one. So that will tell you, that'll lead you in the right direction in terms of which equation you should use. Calculate the solution and round off to the correct number of sig figs. Quite often we use the multiply dividing rule for sig figs. So look at the original question, take a look at the numbers there. Your answer will follow suit. Look at the result. Is it reasonable? So if you do a question and involves a dog traveling at 100 kilometers per hour, something's wrong there because that's not realistic. And then check units again. So we'll look at a couple of examples here, and then the best way to learn this is to actually get in there and do these types of questions. Try to figure out what you need. So runway design. You're designing a small airport for planes. One kind of airplane that you might use in this airfield must reach a speed before takeoff of 100 kilometers per hour, or 27.8. So that's the takeoff speed. So that is the final velocity that the plane must acquire. And that means that you're doing that from when you're at rest. So we know VI is 0. VF is 27.8, and the acceleration of the plane, we're told, is 2.00 meters per second squared. So it increases by 2 meters per second every second. We're also told something else. We're also told that if the runway is 150, can the airplane reach the required speed for takeoff? And if not, what should the length be? So there's a couple of ways we could handle this. I could take a look at, okay, well, I'll use this D value of 100 and see what is my final velocity. If I'm accelerating at this rate, what is my final velocity when I reach the end of the 100 meter, I guess it's 150 meter long runway? So that's what I'm going to do for A. Now, I'm not given anything about time, so I'm going to have to find an equation that has VI, VF, A, and D. And if you scan this list, right there, D, A, VI, and VF. So we're going to use that one. So V final squared is equal to V initial squared plus 2 times A times D. And we're looking for VF, so we can just leave it arranged like this. So VI is 0, so you can see that part's going to disappear. And acceleration is 2.00. And D, we're trying to see, can I reach the end of that and have the acquired speed that I need? So we're solving for VF, so we're going to have to take the square root of each side, right? This part's going to be gone. So this is going to simply be 2 times 2.0 times 150. And when I solve that, multiply, and then take the square root, I get 24.5 meters per second. But I need to reach a speed of 27.8. Therefore, runway is not long enough to reach, what did I need? 27.8 plus 27.8 meters per second. So it's not quite big enough. So what I can do is, okay, well, I'll plug that speed in that I need for here and then rearrange for D to see what is the displacement that I need. What is the length of that runway that I need in order to have this happen? So I need to reach a speed of 27.8. Starting off at 0. Doing this acceleration, 2.0. So over here I'm going to get 4 multiplied by delta D and 27.8 all squared. Didn't figure it out yet. And of course here, to solve for D, I'm going to get D is equal to 27.8 all squared divided by 4. And that works out to be 193.21 meters. If I'm looking at sig figs, with the exception of the 100 here, I have about 3 sig figs, so I can say this is 193 meter sticks. So that's the minimum I need. So therefore, make runway. So we wouldn't make the runway exactly 193. We'd likely do the error. We'd likely make it a little bit longer than 193. So right there, make the runway 193. Okay, take a look at the next question. All right, the next one here. Again, we're looking at something accelerating. A car starts from rest. Boom, right away we know that's true. And accelerates at a constant rate of 10 meters per second squared. Oh, when you have that meters per second squared, that represents velocity. During a 1/4 mile, or that's 402 meter sticks. So that, of course, is D. That's how far I'm going. What is the velocity of the car at the finish line? So I'm looking for VF. I'm given VI. Notice I'm not given anything about time, so guess what? We use that same equation we used earlier. V final squared equals VI squared plus 2AD. So what I can do is I'll set the square root up already. So V final squared is equal to that. Then VF will just simply be the square root of all of that. Of course, this is VI, which is 0, so it's going to disappear. Then I get this and this. So when all is said and done, I think we get 89.666 meters per second. 3 sig figs, 3 sig figs. So VF will be 89.7 meters per second. All right. So what I'll do is I think I'll stop there. In one more video, we'll look at the last example here, and then I'll look at the assignment, and I'll give you some hints there. So hopefully it'll be a little bit easier. All right. We'll see you again.